stuff.
Not familiar.
That's just like what colors can you actually show on a monitor and that sort of thing. How
So
do
is
you
it not
translate
taking
between different colors?
into full like just one after the two?
I don't think it really helps that much. I mean, there's like a little bit at the beginning that's just like the basics.
Hello? So it's totally different, right?
Yeah, it's pretty much totally. I guess the
Hello? Can you hear me?
yeah, I'll do that real quick.
I'm trying to find the microphone. I'm sorry. Okay. At the chapter 12? Not chapter.
Oh, I think apparently it's not supposed to be there.
Excuse me? I think there is a class.
Oh,
I'm sorry.
yeah.
Okay. Good afternoon, everyone. My name is Yandong Guo, and today I'll talk about the Bayesian segmentation. If you have any questions, feel free to email me at eguo1@purdue.edu. And you can call me anytime you want. If you have any solutions, feel free to call me. Okay. First of all, I would like to go through the stuff Professor Bowman has talked about in the last class. Bayesian segmentation. What is the objective of Bayesian segmentation? Here I would like to show you a figure. So here we have the unknown x shown here and the observation y. Y is typically texture feature vector, and x is typically discrete random variables. And we set up constraint on x as Markov random field. And each element of this vector x is indexed by a letter s, xs. So xs is one of the elements in the Markov random field of this x. And given this observation y, we are trying to estimate this unknown x. Since x has a labeling meaning, by estimating x, we can segment this image into different regions. So essentially it's an image segmentation problem. And what is the probability model of this framework? We need to talk about two distributions. One is the forward model, probability model. Py given as is defined as P So this is the definition of the forward model. And we also have a prior model, which is defined as So the forward model describes the physics procedures. Assume we already know the latent variable x. What is the distribution or what is the probability of each of the observation y? And the prior model incorporates the assumptions to be made about this random variable or this latent variable x. I'll give you two examples one example about this forward model and one example about this prior model. So one of the very typical forward model is like this. We have two distributions. Both of them are Gaussian distributions. And if it belongs to the distribution 1, let's say sigma 0 is much larger than sigma 1. If it belongs to the Gaussian distribution, this Gaussian distribution, it will have this random variable y will have a very large variance. And if it belongs to the second Gaussian distribution, s equals to 1, this random variable y will have a much smaller variance. Extreme case is that sigma 0 approaches to 0, and this y will be constant. So this is very typical example of the forward model. And for this prior model, today we'll use Markov random field as a prior model, which is essentially the Gibbs distribution, which means the neighborhood X elements will be forced to be similar with each other. So this is a probability distribution we're going to use for the Bayesian segmentation. With this probability model, we can define different cost functions. And with different cost functions, we can have two estimation strategies. One is MAP, the other one is MPN. So I'll go through the two cost functions very quickly. The first cost function looks like this is the first cost function we are going to use today. What's the meaning of this cost function? This x is the ground truth of the latent variable x. Here, this one x. And x hat is the estimator of the latent variable x. And this x hat is essentially a function of the observation y. And what's the meaning of this cost function? This cost function means that if the estimation or estimator x hat equals to the ground truth x, that this delta is 1, and the cost function has a value 0. But if any element in x hat does not equal to this ground truth x, this cost function has the value 1. This is the definition of this cost function. And with this cost function, we can derive the map estimation. So the map estimation, the map estimator of map estimation is defined as how can we derive from this cost function to this estimator? First of all, we calculate the expectation of this cost function. And calculate the minimizer of this expectation. And the essential strategy used in this minimization is if it's in continuous case. This is the property we're going to use to prove this derivation. I'll write it down for you very quickly. So our objective is to minimize the expectation of this cost function. And how to define it? The definition of this expectation is just this is the definition of expectation. And we put the definition of this cost function into this expectation definition. We can get this equation here by just a substitution. So anyone is following me? And how to minimize this term? The first term is just essentially right? And this term has nothing to do with x hat. Ignore this term. So how to minimize this cost function is equivalent to how to maximize this term. Right? And the maximization of this term is equivalent to this is because whenever x is not equal to x hat, this term is 0. So it's 0 out. The only thing we have here is when x equals to x hat. So this summation is equivalent to this probability. Therefore, the maximization of this term is equivalent to the maximization of this posterior distribution. And furthermore, minimize the expectation of the cost function is equivalent to the maximization of the posterior distribution. This is how we get the math estimation. How we get the definition of this cost function might be problematic. What's the problem of this cost function? So
very strict.
Exactly, it's very strict. It only has two possible values. One is 0, the other possible value is 1. Whenever there is a single element of this x hat does not equal to the ground truth, it has the value 1. But let's say this x hat is very different from this x. The value of this cost function is still 1. It's too conservative. Therefore, we propose a new cost function. Defined as here. So the meaning of this new cost function is that we calculate the summation of all the errors So if there is one difference between the ground truth and the estimate tour, the value of this cost function is 1. If there is two differences, the value is 2. So this cost function is more distributive than the previous cost function. What kind of estimation we can get from minimizing the expectation of this cost function? This is why we need to introduce the second estimation strategy in this chapter, which is called maximizer of the posterior marginal. By minimizing the expectation of this cost function, the estimator of each of the elements can be obtained by this. What is the meaning of this distribution? I'll rewrite the estimator of math estimation to give you a more clear difference between two estimations. At the very beginning, I clarified the notation we are going to use today. S here is the index of the lattice, or the lattice index. Each xs is one element in the random vector X. Okay, so this one is math estimation, and this one is NPM estimation. The estimator of NPM estimation. What's the difference?
Maximizing individual pixels.
Yeah, that's correct. And more precisely, the first equation here, the NPM equation here, this Ps given 1 is the marginal posterior distribution of this xs. This one is the posterior. What's the relationship between these two distributions? If we know a distribution of random vectors, and we want to know the marginal of one element, how we do that?
Sum over like the probability of xs.
Exactly. We just calculate integrals of summation. If it's discrete, we just calculate summation. If it's continuous, we just calculate integrals. Summation any x which does not equal to xs to obtain this marginal distribution. So this is very different from the previous math estimation. And this is definition of the MPF. What kind of advantage we can get from this change?
I'm sorry, like
Go ahead.
the sum is on x. Okay. Yeah. That's fine.
Or if it's continuous, not on the x-axis or the other axis. For the math estimation, if we want to update the physical x-axis, how am I going to do it? If we use ICM method, which we have already talked about yesterday in the last lecture. If we use ICM method to solve map estimation, in order to update each element as that, we fix all the other elements and update the elements we want to update. This is a standard ICM algorithm shown here in this flowchart. But if the current state of all the other elements is not incorrect, estimation of this x-axis will be problematic. But for the NPM method, in order to update a given pixel x-axis, we calculate marginals of the posterior of this x-axis, which means we are considering all the possible states of all the other pixels, not only one state. By doing this, NPM is more stable than the MAP method. This is numerical difference. But also, it has physical meaning difference, which is they have different cost functions. First of all, they have different cost functions. They were obtained by minimizing different cost functions. And because they have different estimate tools, the numerical stable property is different. There are two different. But again, what is the disadvantage of NPM? Exactly. Because for NPM, we need to know the posterior, the marginal of the posterior, not only the posterior. In order to update each of the pixel x-axis, we need to calculate marginals again and again. It's very computationally expensive. If this posterior is Gaussian or is at least belongs to the exponential family, it might be easier to calculate. But still, possibly a lot of computing thought. But if it's not in the exponential family, the cost will be even higher. How to solve this problem? Today, I'll talk about how to optimize NPM cost function. So the method I'm going to use is called sampling method. The first step, we generate a set of L discrete images, each generated from the conditional posterior distribution Px given 1. So we know the posterior distribution. We don't calculate the marginal using this posterior distribution. We just use this posterior distribution to generate samples. And the method we use to generate samples can be any method we've mentioned in the last chapter. An example is Hastings interpolate method. This is a typical method used to generate samples. After we have samples, we calculate the normalized histogram for each of the pixel x-axis using this equation. This is the standard definition of normalized histogram. So what's the meaning of this equation? This means at a given location x, if we have a lot of samples, equals to this value x hat, small x hat, we have a large value here. If we don't have many samples, we have a small value here, or zero value. If we don't have any samples equal to this value, h x hat has a value of 0. And with this normalized histogram, we can estimate each element of MPM estimation using this equation. So maximize the marginal of the posterior can be approximated by maximize the histogram, the normalized histogram. Why this is true? Here is the proof. When the number of samples approaches to infinity, this normalized histogram can almost assuredly, this AS means almost assuredly, equals to the marginal of posterior. This is because the strong law of large numbers. What is the strong law of large numbers? I assume you have 600. So we have a probability space, omega. This is sample, data events, and the probability. And we have one event E here belongs to this event set, and the probability of this E approaches to 1. This is all called convergent, almost assuredly convergent. Okay, here we know how to calculate or how to obtain the estimator of the NPM estimation. I'll revisit it a little bit very quickly. So now we have two estimators. One is MAP estimator, one is NPM estimator. And for this MAP method, it's easier to calculate, but the convergence or the minimizer of this MAP method might not be global minimizer. But we have another method called accumulated annealing to deal with this. For the NPM, it does not have the same issue as MAP, but NPM suffers from the high computational cost. Therefore, we use a sampling method to deal with this disadvantage of NPM. And during the time now, I'll show you another trick to make this MAP estimation even faster, which is multiscale strategy. What is multiscale strategy? It's very simple. For a given image, and if we use the MAP estimation to estimate this given image, what kind of problem we might have? As mentioned, that might not be global, exactly. But if we have a better initial condition, we have more chance to achieve a global minimizer. So how to do that? We downsample this unknown image x, get x1, denote the finest level x0. Then we downsample it again to get an even smaller one, x2. As the first step, we estimate the closest image x2 Then we upsample. We obtain the hat x2. Then we upsample this x2 by upsample. And we use this upsample version of x hat, upsample version of hat of x2 as the initial condition to estimate this x1. We do it repeatedly. Again, when we have estimation of x1, we can upsample this and use the upsample version of this x1 as the initial condition of x0. And this downsample and upsample procedure, typically we will have use a call tree structure. What do I mean by call tree structure? I'll show you a figure. Assuming we have a 512 by 512 image, the first step is to get a 256 by 256 image. This is just 1/4 of the original image, and we do it recursively. And here is a figure to show the probability model of this method. Assuming we have 1, 2, 3, 4, 4 by 4 pixels, which is 15 pixels in the finest image. Then we upsample it to get 4 pixels. Then we get only 1 pixel in the final image. By using this call tree, we get some properties in the cost function. And there is another issue in the cost function, which is the coefficient of the regularizers. Let's say here, beta 2, these two beta 2 control how strong the regularizer is. So T1 and T2 are the regularizer along the vertical directions and the diagonal directions and the horizontal directions. And the beta 2 here controls the how strong the regulator is or how strong the fire is. But if we move from the coarse version to the finer version, we need to update the value of this regulator to make the value of the cost function consistent. In other words, I'll write it down implicitly to make you understand it better. S1. After we finish estimate this x1, we want to estimate x0. Given y and x1. That's data. Fine. T x0. This tx1 and tx0 might have different values. Because we have more pixels here. Even though we use x1 as a initial condition, because we have more pixels, the tx0 has the different value from tx1. But we want to ensure the value of the two regularizers are the same. Therefore, we need to adjust the value of this beta prime accordingly to make the cost function value consistent. So any questions now?
For x1, the initial condition is x2, right?
Yes, it's very like at the very beginning, if we assume we have 3 layers. So x0, x1, x2. Right? And initially is x2. Estimate x2 and use upsample this as the initial condition. Then we estimate x1. Then still upsample this x1 as the initial condition x0. This is the basic strategy. And so the multiscale strategy, I would say it's a trick to make the math estimation faster and more stable. But I think, in my opinion, the most important thing is to understand 2 things. One is MAP, one is MPM, and how we get them. How to define a cost function, and how to obtain the estimation strategy by minimizing cost function. And what's the difference between MPM and MAP? And what is the algorithm to optimize the 2 cost functions? And if we have better understanding of MAP and MPM, the following 2 subsections are much easier for you guys to understand. So the following 2 sections, we have 2 sections. One is joint segmentation and reconstruction. And 12.3 is EM and TN. So for this subsection, we make use of the math estimation to solve a reconstruction problem and segmentation problem simultaneously. And for the third subsection, we use MPM structure to estimate the parameters in the physical model. So I talked about the joint segmentation and reconstruction. Okay, what is the reconstruction? I'll review the reconstruction described in chapter 7 very quickly to give you a better understanding. So the observation 1 obtained by a linear projection defined by A by the unknown up to the unknown x plus some more. So this is a very traditional classical forward model in the reconstruction problem. And how to estimate x from this y. Estimate equals to we have 2 terms. This term is try to fit the unknown x to the observation y. This is likelihood term. And this is regularized term. I'll rewrite here. This is regularized. What's the meaning of this regularized? It's a delta function. If the values they have the same value, it ensures the value of 2 pixels to be similar, or force from that to that direction. And in this subsection, we introduce another constraint on this unknown x. This x, in the previous chapter, in the chapter 7, this x has a continuous value. Assuming that we have n pixels in this x, we have the feasible set of this x is Rn. with quite large set. And we need a lot of operations to get a good estimation or good estimators onto this unknown. But if we constrain this X to be discrete, let's say X belongs to n discrete values, much smaller visible set onto the unknown. Assume we have a vector C defined as C0, C1, Cn minus 1. If the value of X has to equal to one of the elements in this vector, X has a much smaller visible set, right? And Xx, which is the S element in the vector X, equals to Vs. Z is the index of the possible values. I'll draw a figure to illustrate in more clearly. So we have X, right? X is the image we estimated. This image has to equal to two values. One is like 0.65. One is 0.75. So m equals to 2. We have the vector C equals to 0.65, 0.75. And we have a labeling variable Z here. If Z equals to 0, Vs equals to 0, Xs equals to C0. If Vs equals to 1, Xs equals to C1. Which means we have a labeling image, V, here. And the possible value of this labeling image is either 0 or 1. Is this clear? Does everyone understand this? So this is very important. After we understand the settings of this problem, the following stuff in this section is very simple. Okay, we have these settings. With this setting, we can estimate the segmentation and the reconstruction simultaneously. What is the cost function looks like? So here is the cost function. What's the difference between this one and the previous one? I'll write down the previous one here. This is a cost function of the previous reconstruction. In the previous setting, X could be any value, but in this setting, X has to equal to one of the elements in the vector C. But we don't know which one. Z is the index of the element. And here in this term, in the previous reconstruction, we want to ensure the values of the neighborhood pixels to be similar. But here, in this setting, in the cost function in this section, we want to ensure not only the difference is smaller, we want to ensure the labeling is the same, is identical. Whenever the label is different, this delta has a value 1. want to make similar regions group together, or same the region with same labels group together. How to optimize this plot function, and how many unknowns need to be optimized in this plot function? What are the unknowns? Do we know phi? Y is observation. C is just a regularization, right? We assume x equals to certain values, but we don't know what value. So C is unknown. Do we know the index V? Probably don't, because we need to segment the image simultaneously, right? So the C and V all come from the unknown X. Therefore, there are two sets of unknowns in this plot function. One is C, one is V. Any questions? And here is the algorithm to optimize V and the C. The first step is to initialize V and C. Apparently, we need initialization. And this is very similar with the previous algorithm in the IC algorithm used in chapter 7. We calculate the error E by this equation here. This is where the estimation is not consistent with the observation 1. And by using this, we can estimate the C and V using alternating methods. So, any questions?
How are you estimating the C and D?
Good question. So here, assume we know C, we already know C. Because we have initialization, we have like random guess as the initialization condition. Assume we know C. We can obtain V by minimizing this plot function, right? If we move this plot function, original plot function here, assume we already know C. This is nothing but a segmentation problem we just described. It's identical with the map estimation we just talked about 20 minutes ago, right? And assume we already know Z, how fast into C. If we already know Z, if we go back to this plot function, if we already know Z, this term doesn't matter. So this term is all about Z. We only need to minimize this term. So we can even get an analytical solution on C by minimizing. It's just a least square problem to be solved. So I think this is all for today. Today we talked about two estimation strategies. One is MAP estimation. The second one is MTM estimation. And then we also introduced the T, which is called multiscale strategy to make MTM faster and more stable. And we apply map estimation, joint map estimation as a simultaneous optimization for reconstruction and segmentation. Thanks a lot. If you have any questions, here's my email address. So, thanks.